Now we want to find out the dimension of the key for the required power transmission. In that case, first you have to find out what is the force acting on the sunk key. Now the sunk key is fitted here with respect to the shaft and the hub, which can be a straight key or in a tapered key driven in a place. Because of this, there is a compressive stresses are produced in the key. So this represents the compressive stresses produced due to the tight fitting of a straight key or a tapered key. So let's call this one as a F1. So F1 represent here the compressive force due to the tight fitting, and then the power is transmitted here. Power is same as equal to 2 pi into rotational speed n multiplied by torque T divided by 60. And this torque will develop the additional force that equal to F2. So torque is given as F2 multiplied by D by 2. So this force is same as equal to F2 is due to the torque transmission. So when the key is used in transmitting the torque from the shaft to the rotor or the hub, the two type of forces will act. The forces due to the fit of the key in a key way, as in tight fitting straight key or in a tapered key driven in a place. This forces produces the compressive stress, that is F1, in the key, which are difficult to determine in magnitude. Secondly, the forces due to the torque transmitted by the shaft, that is T is equal to F2 multiplied by D by 2. This forces produces the shearing and the compressive stresses, which are also called as the crushing stresses in the key. And hence the distribution of the forces along the length of the key, that is along this length, is not uniform because the forces are concentrated near the torque input end, and the non-uniformity of the distribution is caused by twisting of the shaft within the hub. So the force F2 and F1 both are variable along the length equal to L, which one is the width of the hub. So calculation of F1 is much difficult, whereas F2 we can calculate very easily. So we have to neglect the force F1 and you have to consider only the force F2. So in designing a key, the forces due to the fit of the key are neglected, and it is assumed that the distribution will be uniform along the length of the key. That is the assumption. So we are not going to consider the forces due to the fit, that is F1 will neglect and only will design on the base of F2. So whenever we are going to design a key, the forces due to the fit of the key are neglected, and it is assumed that the distribution of the force along the length of the key is uniform. So distribution you have to take as a uniform along the length of the key. We'll design the key for crushing as well as for shearing. For this one, we'll consider here one rectangular key which is fitted in between the shaft and the hub. Let T is the torque transmitted by the shaft. So the torque transmitted by the shaft is represented by T is same as equal to F multiplied by the diameter divided by 2. So we have D by 2. So we'll consider here a rectangular sunk key. Let's consider here this point is same as equal to A. The other point will be equal to B. So AB will divide the key into two halves. Let's say this point is equal to C. This point is equal to D. So this force F is acting on BD and for AC. That is the bottom portion of the key. To visualize here the more clear, so we'll develop this figure. This point is same as equal to A. This point is same as equal to B. This top point we are representing as D. And this bottom point we are representing as C. This force is acting on the upper half of the key, and this force is acting on the lower half of the key. Because of these forces, the top plane will shift on the bottom plane. In this figure, we'll find here the top plane has been shifted over the bottom plane. That is, a shearing takes place. Shearing is taking place over this area, which one is the same area on the top surface. So let's say W represent here the width of the key, T represents the thickness of the key, and L represent the length of the key L. So in this case, this width is same as equal to W. We have a length equal to L. So the area on the top plane as well as the shearing area is one and same. So here we have this area will be the shearing area. So shearing area will going to represent by AS, and the value of the shearing area is product of W multiplied by L, that is width multiplied by length L. So as shown in the figure, the shaft applies the force F on the key, that is this force is equal to F, and the key applies equal and opposite force on the hub. Therefore key is acted upon by two equal forces of magnitude equal to F. One is applied by the shaft on the lower portion and other because of the reaction of the hub on the upper portion. As these two forces are not in the same plane, they constitute a couple which tries to tilt the key. Therefore equal and opposite forces are developed, also act on the key, which provide a resisting couple that keeps the key in position. Now the exact location of the force F it is not known, so to simplify the analysis, it is assumed that the force acts tangential to the shaft. If tau allowable is a shearing stress, that is a shear stress, which is same as equal to SYS divided by factor of safety, SYS divided by factor of safety. Yield stress in shear divided by factor of safety, that is tau allowable. So in this case we develop a shear force, that is also called as the shear strength of the key, is given as Fs, is same as equal to the shear stress multiplied by shearing area, that is tau allowable multiplied by the shear area, which is width multiplied by L. So let's say equation number 1. When the shaft pushes the key, in that case the lower portion will be get crushed against the hub. So this area, that is this area, which one is the bottom area, is called as the crushing area. So we have crushing area will represent as AC, is this area. This area is same as T by 2 multiplied by length L. So we have T multiplied by L divided by 2. The allowable crushing stress is represented by sigma CR. In that case we can find out the crushing strength of the key. So crushing strength will represent as FCR is equal to the crushing stress multiplied by the crushing area. Crushing stress will represent as sigma CR, and we have crushing area is equal to T multiplied by L divided by 2. So these are the two types of the stresses of the strength we have produced. One is a shear and one is crushing. As far as the design is considered, design is always based on the lower value of shear and the crushing strength. So on this area the crushing is taking place. So this area is same as equal to the length multiplied by thickness divided by 2, because we assume here we have a equal portion in both the hub and the shaft. So this one is nothing but our crushing area AC, and in between this, that is the plane AB, represent here the shear area. So we have shearing area is equal to W into L. So we have shear strength will be equal to Fs equal to tau allowable multiplied by the shear area W into L, and we have crushing strength is represented as FCR, crushing stress multiplied by crushing area, which is T multiplied by L divided by 2. As we know that the torque transmitted by the shaft is given as force multiplied by the radius, which is d by 2. So the maximum torque that can be transmitted due to the shear force is represented by ms and is same as Fs multiplied by d by 2. Fs multiplied by d by 2. We know the shear strength of the key, that is tau allowable multiplied by W multiplied by L. In this case we'll get the maximum torque that can be transmitted due to shear is Fs, which is equal to tau. I will just write here tau instead of allowable. So this one you have to read as a tau allowable multiplied by W multiplied by L multiplied by d by 2. Let's say equation number 3. Similarly, we can calculate here the maximum torque that can be transmitted due to crushing, which will represent as MCR is same as force, that is a crushing force multiplied by diameter divided by 2. So we have maximum torque that can be transmitted due to the crushing force is MCR. We have crushing force is sigma CR multiplied by T multiplied by L divided by 2. So we have sigma CR, allowable crushing stress, multiplied by T multiplied by L is divided by 2, is further multiplied by D by 2. Let's say this one is equation number 4. So if the key is equally strong in the crushing and shearing, in that case we can equate Ms, that is the maximum torque that can be transmitted due to shear, with the maximum torque that can be transmitted due to crushing. So if we equate Ms with MCR, means we have equal, means the key is equally strong in crushing as well as shearing. We have Ms is given as tau multiplied by width multiplied by length multiplied by D by 2, and we have maximum torque due to crushing is sigma CR multiplied by T multiplied by L divided by 2 and further multiplied by D by 2. So in this case D by 2 and D by 2 will cancel out. Even the length will also get cancelled out, and we can find the ratio of width to thickness. So the ratio of the width of the key W to thickness T is same as equal to sigma CR divided by 2 sigma CR divided by 2 divided by tau. So this result we obtain if the key is equally strong in crushing and shearing. Now we know here the permissible crushing stress for a key material is at least twice the permissible shear stress. That is, we know here that we have permissible value of the crushing stress is approximately equal to 2 times the permissible value of the shear stress. So if I substitute sigma CR is equal to 2 times of tau in equation 5, so equation 5 will imply width of the key divided by the thickness of the key is equal to sigma CR, which will write as 2 times the permissible shear stress divided by 2 times the permissible shear stress. So tau and tau is get cancelled, 2 and 2 is get cancelled. So whenever we are equating the maximum torque that can be transmitted due to shear is same as the maximum torque that can be transmitted due to crushing, in that case we have W is same as equal to T. It means that instead of using the rectangular section, we must use the square section where the W is same as equal to T. This is true when the maximum torque MC due to crushing is same as equal to the maximum torque transmitted due to shear. So in general, the key is strong in crushing as compared to in shearing, and hence the design is always based on the shearing. We are also familiar here that the torque transmitted by the shaft is given as pi by 16 into diameter cube of a shaft multiplied by allowable shear stress. Now using the value of the torque transmitted by the shaft and the maximum torque that can be transmitted due to shear, we are able to find out the length. So in order to find the length of the key to transmit the full power of the shaft, the maximum torque that can be transmitted due to shear is equal to the torsional shear strength of the shaft, which is equal to pi by 16 d cube tau. So we can equate here the equation number 3 and 6. So we have Ms is equal to T. Ms is same as equal to tau multiplied by width multiplied by length multiplied by D by 2 is equal to, and the torsional shear strength is given as pi by 16 multiplied by D cube multiplied by tau. Here we have assumed that the material that is used for the key and the shaft is same, then the tau value will be same. Otherwise, for different material, we have to take the different value of tau. Let's solve for L here. So tau is get cancel here on both sides. This 2 is get cancel here and we left here with 8. This D will be get cancel here and we are, instead of cube, we have D square. So in this case, we'll get W into L is same as equal to pi by 8 into d square. The standard dimension of the width of the key is same as equal to W is d by 4, where d is the diameter of the shaft. So we'll take the width of the key W is same as equal to d by 4. So this W we can replace as d by 4 multiplied by L is equal to pi divided by 8 multiplied by d square. So again the value of d will be cancelled and 1 d is left here. This 4 is cancelled and 2 is left. So if we equate the maximum torque that can be transmitted due to shear is equal to torsional shear strength of the shaft, and we assume the same material of the shaft and key, and the width is equal to d by 4. In that case the length of the key will be equal to pi multiplied by d divided by 2. In this fashion we can calculate the length of the key. And if the permissible crushing stress for the material is equated with the shearing, in that case we'll get here W value is same as equal to T, assuming sigma crushing is equal to 2 times of tau. But if the values are different, then you have to use the equation number 5. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.